Chapter 2: Simple stress and strain. Two criteria on which machine elements are designed. Strength: maximum stress that a material can withstand without failure. Maximum stress due to external loads less than allowable stress, then failure occurs. Allowable stress can be sigma y, yield stress, or sigma u, ultimate stress. Failure: for brittle absolute fracture, ultimate stress is failure stress. Example: concrete M20, concrete M20, sigma U is equal to 20 megapascal. Ductile yielding, yield stress. Steel yield stress is failure stress. Example: steel, sigma Y is equal to 200 MPa. Stiffness, resistance against deformation. Maximum deformation due to external load less than allowable deformation. Allowable deformation depends on application, fixed by engineer. Stiffness means resistance against deformation. Okay, strength and stiffness are the two basic design criteria. The stress is the internal resisting force developed at a point against the externally applied load. If P is applied here at a section, cross section XX, internal resisting forces P1, P2, P2, so on will be developed. Let's consider a small cross sectional area delta A. With there delta P, internal resisting force will be developed. P1, P2, Pn, so on. Those are internally resisting forces. By static equation, P1 plus P2, so on, Pn equal to P. By definition of stress, sigma is equal to limit delta A tends to 0, delta P by delta A. Sigma is equal to dP by dA. Integral sigma dA is equal to integral A dP. Integral sigma dA is equal to P. Sigma into A is equal to P. Sigma is equal to P by A due to first basic load. Assumption: the value of stress is same at all points of cross section. Saint-Venant principle. Here, Saint-Venant principle, like in some interviews, they're asking what is Saint-Venant's principle. You should not be confused with what Saint-Venant's theory that comes in theory of failure. That comes like in theory of failures. Saint-Venant's principle is different. The value of stress is same at all points of cross section. For example, if you see if you apply in force P here, there will be a lot of stresses here at different points, but it is considered that the value of stress is same at all points and represented like this. The value of stress is same at all points of cross section. Everywhere it will be sigma itself. Everywhere it will be sigma. That is Saint Venant's principle. Like, it is important question for ISRO interview. Units: Newton per meter square, Pascal. Kilopascal is equal to 10 cube Pascal. Megapascal is equal to 10 power 6 Pascal is equal to 10 power 6 Newton per meter square is equal to 1 Newton per mm square. Gigapascal is equal to 10 cube Megapascal. Notes: stress doesn't depend on type of material, it only depends on amount of external load and area which is going to resist it. Stress will always develop in a direction in which external load is applied, but strain may come in direction with respect without having external load in that direction. Stress doesn't depend on type of material, but it only depends on force and area, as we can see from the formula. Stress will always develop in the direction, but strain cannot may not come in that direction because there can be in other directions too. Example, here if we apply P in this direction and P in this direction, there will be a movement. Sigma x is not equal to 0. Upper layers will be in upper layers will be in compression. Lower layers, this is neutral axis, lower layers will be in tension. Sigma x is not equal to 0. Sigma y is equal to 0. Sigma z is equal to 0. If we place If a block is just given 5 newtons in one direction, it is free at other end. There is nothing like fixed or anything, so there won't be any internal resisting force. So sigma is equal to 0, stress will be 0. This is also an interview question. Uh, it will just move with acceleration 5 by mass. If 5 Newton is applied in this direction and in this direction both, at any cross section there will be resisting force. Sigma is equal to 5 Newton per meter, 1 meter square. Area is given as 1 meter, it will is equal to 5 Pascal. If 5 Newton and 10 Newton, if 5 Newton is applied on this side and 10 Newton is applied on this side, sigma will be equal to 5 Pascal, as 5 and 5. Remaining 5 it will move, but due to 5 Newton there will be sigma of 5 Pascal. Difference between stress and pressure. Stress is, this is also interview question, internal resistive force per area. Pressure, external force per area. Can act Stress can act perpendicular or parallel to the surface, but pressure acts perpendicular to the surface only. This is tensor. Stress is tensor. Pressure is scalar. Classification of stresses. Normal stress, elongation or contraction. Direct normal stress or axial stress. If a beam is fixed like this and a force P is applied on a cross-sectional area A, then stress sigma is equal to P by A. Indirect normal stress or bending stress. A moment is applied like this, then this equation, we will use this equation, m by I n a is equal to sigma by y is equal to E by R. Here E is Young's modulus, R is radius of curvature, sigma is stress, bending stress, y is distance from neutral axis, m is bending moment that we have applied, I and a is moment of inertia about neutral axis. Shear stress distortion. Shear stress in beams. uh, if a beam with circular cross section is like this, then if we apply a force V in this direction parallel to the cross section, then there will be shear stress generated. Tau is equal to VA y bar by INA B. Here B is width, I is moment of inertia about neutral axis, V force, A is cross sectional area, y bar is distance from center. Indirect shear stress or torsional shear stress. If a beam with circular cross section is like this, then if we apply torque T by J is equal to tau by R is equal to G theta by L. G is modulus of rigidity, theta is a twist angle, L length of beam, tau shear stress, R distance from center, like around the center, T torque, J polar moment of inertia. Now coming to strains. Normal strain epsilon, axial or linear, also known as axial or linear strain. Epsilon is equal to change in dimension by original dimension, unitless. Epsilon is equal to 10 micron is equal to 10 into 10 power minus 6. Epsilon x is equal to delta L by L. Epsilon y is equal to delta H by H. Epsilon z is equal to delta B by B. Delta is equal to final minus initial. uh, According to coordinate system we will decide strains, normal strains. Okay, shear strain, pi or gamma, it is change in angle between any two planes which are originally at right angle. If we consider a small element A B C D in this big element initially which is at right angle A B C, and it finally it is changed to A dash B C dash. The change in angles theta 1 theta 2, pi shear strain is equal to mod of theta 1 plus theta 2. Volumetric strain epsilon V is equal to epsilon x plus epsilon y plus epsilon z is equal to change in volume by original volume. Stress system 3D. This is representation of stress tensor. Sigma xx will be in this direction, sigma yy will be in this direction, sigma zz will be in this direction, which will be obvious. Tau xy will be in this direction, which is in plane of x and y. Tau xz will be in this direction. Tau yz will be in this direction. Tau yx will be in this direction. Like sigma yy, which will be linked with tau yz. Here y is linked to sigma yy, then z will be in this direction. Sigma is equal to sigma xx tau x face tau z tau xz x face. Yes, tau x yx sigma yy tau yz y face. Tau zx tau zy sigma z face. In this, if you go in this direction, then these are directions: x direction, y direction, z direction. Sigma, then free body diagram will be like this: sigma sigma. If tau is applied like this, then free body diagram will be, there will be tau in these directions. These two, these are complementary stress, complementary stresses. By moment equation, tau bc into a, which is force here, is equal to tau dash ab into c, which will be here. By moment equation, balance equation, tau is equal to tau dash, complementary shear stress. Complementary shear stress, tau xy is equal to tau yx. Tau yz is equal to tau zy. Tau zx is equal to tau xz. Tau xy is here, tau yx is here. These two will be equal. These two. So here these two will be equal. These two. So according to complementary shear stress condition, the magnitude of shear stress must be same or same on any two mutually perpendicular planes. The direction of shear stress are either towards corner edges or away from corner in order to produce a balancing couple. The stress matrix is symmetric due to moment equilibrium condition. Plane stress or 2D stress. Example: beams, shaft, thin plates. Sigma is equal to sigma xx tau xy tau yx sigma yy. 1D stress. Example: bar, rod, column. Sigma xx 1 by 1. Strain system. Sigma xx will be replaced by epsilon xx. Sigma yy will be replaced by epsilon yy. Sigma zz will be replaced by epsilon zz. Tau xy will be replaced by gamma xy by 2. Tau x theta 1 theta 2. Gamma is equal to theta 1 plus theta 2. Gamma is equal to theta plus theta is equal to 2 theta. By symmetric, theta 1 is equal to theta 2, theta is equal to gamma by 2. So gamma is equal to gamma xy by 2 plus gamma yx by 2 due to tau xy due to tau yx. Like, this is the explanation why we are using by 2 in this tensor representation. Epsilon is equal to epsilon xx gamma xy by 2 gamma xz by 2 gamma yx by 2 epsilon yy gamma yz by 2 gamma zx by 2 gamma zy by 2 epsilon zz. 2D strain or plane strain. Epsilon is equal to epsilon xx gamma xy by 2 gamma yx by 2 epsilon yy. Example: thick bodies. Stress strain system: total number of sigma or epsilon components, independent number of sigma or epsilon needed, epsilon component needed. 3D. 3 into 3 9. 6 3 sigma 3 tau. Independent, those are independent needed. If 2D, 2 by 2 4. Here 3 independent are required: 2 sigma 1 tau. 1D 1 by 1 1 sigma required. Now coming to elastic constants. Young's modulus E. By Hooke's law, sigma is directly proportional to epsilon. Sigma is equal to E epsilon. E is equal to sigma by epsilon. E is modulus of elasticity, represented in megapascal, units of megapascal or gigapascal. In this diagram, we can see sigma, epsilon, aluminum is here, steel is here, diamond is here. And a slope of these diagrams will give Young's modulus. Young's modulus of steel is 200 gigapascal, and Young's modulus of aluminum is 70 gigapascal, which is less than steel. And Young's modulus of diamond is 1200 gigapascal, which is higher than steel. Here it is. Find sigma. Yeah, I think this is previous gate question. E1, E2, this section has Young's modulus of E1, this section has Young's modulus of E2. Here P and P are applied, forces are applied, cross sectional area is E. A. Find sigma. Sigma is equal to P by A, which is independent of E, so answer is A, P by A. Shear stress, shear or rigidity modulus, shear modulus or rigidity modulus represented by G. Tau is directly proportional to gamma up to proportionality limit. Tau is equal to G gamma. G is equal to tau by gamma, megapascal or gigapascal. G less than E. Bulk modulus K, defined only for hydrostatic pressure condition. Sigma y is equal to sigma x is equal to sigma y is equal to sigma z is equal to P. K is equal to P by epsilon v is equal to P by delta V by V. Delta V is equal to PV by K. Here P is equal to pressure. One question from ESE workbook. These are given conditions. What is delta V? Delta V is equal to PV by K. K is equal to P by epsilon V is equal to P by delta V by V. Delta V is equal to PV by K. These all will be given in words in question. You just have to write what is given and then we can find delta V from this formula. Longitudinal strain. It is normal strain along direction of load. Lateral strain. It is normal strain in a direction which is perpendicular to direction of load. Every longitudinal strain is associated with two lateral strain. The nature of longitudinal strain and lateral strain are opposite in nature. For example, if we apply tensile in x, then x direction, then there will be compression in y and z direction. That is general case. Poisson's ratio mu or 1 by m. Mu or 1 by m. If we apply a force in x direction P, then epsilon x longitudinal strain, epsilon y, epsilon z lateral strain. Mu is equal to minus lateral strain by longitudinal strain. Mu is equal to minus epsilon y by epsilon x. Mu is equal to minus epsilon z by epsilon x. Epsilon y is equal to epsilon z, isotropic and homogeneous. Mu is same in both directions. Note minus 1 less than or equal to mu less than or equal to 0.5. Mu less than 0 negative. Oxidative material made in lab. Anti-rubber material. These are not real, like made in lab. 0 less than or equal to mu less than or equal to 0.5 for general material. Mu is equal to 0 cork. We use it for caps of some bottles. Mu is equal to 0.1 to 0.2 concrete. Mu is equal to 0.3 steel. Mu is equal to 0.25 to 0.33 engineering material. Mu is equal to 0.499 rubber. Mu is equal to 0.5 for all incompressible material. Delta V is equal to 0. V final is equal to V initial. The above listed values of mu are varied within elastic limit. In plastic range metal forming, most of materials will have mu is equal to 0.5. Mu is equal to 0.5. Like in metal forming, volume will be constant, so mu is equal to 0.5. Relation between elastic constants, E is equal to 2g into 1 plus mu, E is equal to 3k into 1 minus 2 mu. Example, steel, mu is equal to 0.3, E is equal to 2g into 1 plus 1 0.3 is equal to E, G is equal to E by 2.6. E is equal to 3k into 1 minus 2 mu, K is equal to E by 1.2. From this we can understand that E greater than K greater than G. E greater than K greater than G. Question, if E, K and G denote their usual meaning, then for a general material, which one of the following can be possibly true? Before we got that E greater than K greater than G. So this is wrong. This is wrong. This is wrong. A can be an no, greater than or equal to, just for this case, this is valid. For everything we have to check. 2g into 1 plus mu is equal to 3k into 1 minus 2 mu. In place of g we can place 2k. Mu is equal to minus 0.1, which can't be true. If we place e is equal to 3k into 1 minus 2 mu, mu is equal to 1 by 3, 0.3, which is in range of 0 and 0.5. So B can be a correct answer. See, this is only for this example. For everything we have to check value of mu if anything can be true. Okay, material homogeneous plus isotropic, minimum number of elastic constants needed 2, orthotropic 9, anisotropic 21. Homogeneous plus isotropic, the one we are studying before. If we know any two elastic constants, we can find out the remaining two. So number of number of elastic constants required 2. For orthotropic 9, anisotropic 21. Hooke's law. By Hooke's law, sigma x is equal to E into epsilon x. Epsilon x is equal to sigma x by E. Mu is equal to minus epsilon y by epsilon x. Epsilon y is equal to epsilon z is equal to minus mu epsilon x is equal to minus mu sigma x by E. Minus mu sigma x by E. General Hooke's law. Like this is for 1D. If 1D only sigma x exists. General Hooke's law, it is used to find normal strain when stress is acting more than one direction. Sigma x, like if only here only sigma x is acting. If more than one stress are acting, sigma x, sigma y, sigma z in x and y z directions, then epsilon x is equal to sigma x by E minus mu sigma y, mu sigma y by E minus mu sigma z by E. Epsilon y is equal to sigma y by E minus mu sigma z by E minus mu sigma x by E. Epsilon z is equal to sigma z by E minus mu sigma x by E minus mu sigma y by E. A plane stress system need not necessarily will result into plane strain system. Like if you apply in sigma x, there can be epsilon y, epsilon z also. Now that is what this sentence means. Okay, now coming to a question. A bar of elastic material is subjected to a direct compressive stress sigma 1 in longitudinal direction. Suitable lateral compressive stress sigma 2 is applied along each of other two lateral directions to limit the net strain in each of the lateral direction to half of the magnitude of what it could be under sigma 1 acting alone. If mu is Poisson's ratio, then find sigma 2. Let's consider two cases. If sigma 1 is only sigma 1 is acting, epsilon 2 is equal to as it is compressive plus sigma 1 by E. Epsilon 3 is equal to plus mu sigma 1 by E. Case 2, both sigma 1 and sigma 2 are acting. Sigma 2 is also compressive. Epsilon 2 is equal to minus 2 minus sigma 2 by E plus mu sigma 1 by E plus sigma 2 by E. Epsilon 3 dash is equal to minus sigma 2 by E plus mu sigma 1 by E plus sigma 2 by E. Epsilon 2 dash is equal to half epsilon 2, as this is the given. After solving, we will get sigma 2 is equal to mu sigma 1 by 2 into 1 minus mu. Another question regarding same like page number 26 in our workbook, same like they will give some conditions, we have to find relationship, we will get like this. Another question, epsilon L is equal to, we can find it from given sources, then we have to find epsilon D is equal to minus mu epsilon L, from that we can find delta D. Okay, another question, a square plate of dimension L by L is subjected to a pressure P is equal to 250 megapascal. Assume plane stress condition. The deformed shape is also square of dimension L minus 2 delta. If L is equal to 2 meters and delta is equal to 0.001, then mu is equal to question mark E is equal to 200 gigapascal. Here it is given that it is subjected to pressure of 250 megapascal, then sigma x is equal to sigma y is equal to minus 250 MPa, and then we can use this equation epsilon x is equal to sigma x by e minus mu sigma y by e. As it is square plate, if there is delta in this direction, there will be delta here also, then the final shape will be L minus 2 delta. L minus 2 delta, then L minus 2 delta minus L by L is equal to sigma by E into 1 minus mu, as sigma is same, and from that we can get mu. A uniform bar lying in x direction is subjected to pure bending. Which of the following stances represent strain variation when bending is about z axis? When bending is about z axis. Bending is about z axis. Sigma x not equal to 0, sigma y is equal to 0, sigma z is equal to 0. Epsilon x is equal to sigma x by e, epsilon y is equal to minus mu sigma x by e q, the epsilon z is equal to minus mu sigma y by e. Same sigma y, epsilon y and epsilon z are both same. Application of general Hooke's law. Case 1, rectangular bar subjected to 3D stress. V is equal to volume is equal to LBH by partial differentiation. dV by V is equal to del dL by L plus dV by V plus dH by H. Like if we differentiate by partial differentiation like this and we divide by volume, we will get this. Then from that we can get epsilon V is equal to epsilon x plus epsilon y plus epsilon z. By general Hooke's law, epsilon V is equal to 1 minus 2 mu by E into sigma x plus sigma y plus sigma z. If mu is equal to 0.5, epsilon V is equal to 0, delta V is equal to 0, Vf is equal to Va incompressible. For hydrostatic pressure condition, epsilon V is equal to 1 minus 2 mu by E into P plus P plus P. E is equal to 3 into P by epsilon V into 1 minus 2 mu. E is equal to 3K into 1 minus 2 mu. Here P by epsilon V can be replaced by K. Solid circular shaft, epsilon V is equal to epsilon L plus epsilon D plus epsilon D. Epsilon V is equal to epsilon L plus 2 epsilon D. Epsilon D is diametric or circumferential or hoop strain D in this direction. Solid sphere, epsilon V is equal to 3 epsilon D. Axial deformation. Case 1, prismatic bar, P is applied, then L. Sigma is equal to P by A. Epsilon is equal to delta by L. By Hooke's law, sigma is equal to E epsilon. P by A is equal to E delta by L. Delta is equal to PL by AE is equal to sigma L by E. Condition in which this formula is valid. Member should be prismatic. Axial load must be constant along the length. Material should obey Hooke's law. P is equal to K delta. P is equal to AE by L into delta. AE by L, axial stiffness of bar. Axial stiffness K directly proportional to E and A. and inversely proportional to 1 by L. 1 by L. AE, axial rigidity of bar. AE by L, axial stiffness of bar. AE, axial rigidity of bar. Case 2, non-prismatic bar, stepped bar. P and P are applied. There are three different cross-section areas, three different lengths, three different Young's modulus. At every section, we can take like P, then internal resisting force. There will be another P. Then delta 1 is equal to PL1 by AE, A1 E1. Delta 2 is equal to PL2 by A2 E2. Delta 3 is equal to PL3 by A3 E3. Delta is equal to delta 1 plus delta 2 plus delta 3. How to find out axial load which is responsible for axial deformation and axial stress generation. The axial load at any section is the summation of all internal resisting force at that section in axial direction, or the axial load at any cross section is summation of all horizontal forces either from right or from left of section with proper sign. Sign convention based on direction used in static equations. If it is in this direction, then negative. If it is in this direction, then positive. Uh, if it is in this direction, then positive. If it is downward, then negative. Smiling bending moment. If it is a smiley position, then positive. If it is in this direction, positive. If it is in this direction, negative. Based on deformation used while calculating basic loads. PPXX AL is equal to plus P. Axial load here, axial load is equal to plus P, axial load is equal to minus P. If this is positive, then this is negative. If this is positive, then this is negative. That is it. There is nothing too much meaning in this. If this is positive, this is negative. If one is positive, one is negative. Here, based on deformation, we can say that axial load plus P minus P. Okay. For the given stepped bar, this is given, then find the value of x, total axial deformation and stress in each segment, and also draw axial load diagram. 5p plus 3p is equal to 2p plus x. Like in stress in this direction, if you consider whole bar, it should be in equilibrium. So it should be in 5p plus 3p is equal to 2p plus x. X is equal to 6p. Axial load diagram, from here to here there will be 5p. From here on, 5p minus 2p, so 3p will be here. From this length to this cross section, and then from here on, 3p minus x. 3p, here x is 6p, so it will 3p minus 6p, which will be equal to minus 3p. From here to this section, it minus 3p will be the force. Deformation in first bar, delta 1 is equal to 5p is the force, 5p into 2l is the length by 6a cross section into E, and then delta 2 is equal to 3p is the force, 4a cross section in L length E. Okay, similarly delta 3 minus 3p into L by a by 2 into E. Delta is equal to delta 1 plus delta 2 plus delta 3, 10pl by 6ae plus 3pl by 4ae minus 6pl by ae. If sigma has to be calculated at each section, sigma 1 is equal to 5p by 6a, sigma 2 is equal to 3p by 4a, sigma 3 is equal to minus 3p by a by 2. For given prismatic bar, find out p by f so that deflection at point C will become 0. P by F. P and F are forces. Okay. uh, BC section, only P will be acting. Delta BC is equal to PL by AE. At the AB section, P minus F will be acting. Delta AB is equal to P minus F into L by 3AE. 3E. Here 3 is given. So the condition is the deflection at point C. Here deflection should be 0. So delta BC plus delta AB is equal to 0. PL by AE plus P minus F into L by 3AE equal to 0. Then 4P is equal to F. P by F is equal to 1 by 4. Okay. If, always consider tensile and add deformation equal to and equal to 0. Okay. Prismatic bar is fixed between rigid supports along its length as shown in figure. Find out reaction forces at support A and D. A at supports A and D. If RA is like this, RD is like this, then it is fixed. Total deformation should be 0. That will be the condition. Okay. First, by static equation, RA, if we remove these walls, then RA RD should be like this. By static equation, RA plus W is equal to RD plus W. RA is equal to RD. That is by static equation. Compatibility constraint situation, because of rigid walls, delta AB plus delta BC plus delta CD is equal to 0. From this cross section we have to move on in this direction. RD into L by 3 by AE plus RD minus W into L by 3 by AE plus RD into L by 3 by AE is equal to 0. From that, RD minus W is equal to 0. RD is equal to W by 3. From workbook, similar question has been taken, and like some stress conditions are given, Pmax. So from that, Pmax is given. Another question, sigma crushing into punch area is equal to tau into shear area. Sigma c into pi by 4 d square is equal to tau into pi dt. Okay, now consider for circular tapered bar. From cross section diameter varies from D1 to D2. Let's consider a small section at a distance x where diameter is dx. Then dx will be, as the diameter is increasing linearly, dx is equal to d1 plus d2 minus d1 by l whole of into x. P dx integral delta L is equal to integral 0 to L P dx by pi by 4 dx square E. If we integrate, delta L is equal to 4 P L by pi d1 d2 E. Square tapered bar, similar process, like we have to take width at a point, then we will get delta L is equal to PL by ABE. PL by ABE. If you want, you can cross check by replacing A is equal to B. Here also D1 is equal to D2. We will get the same as before. Rectangular tapered bar with constant thickness. Delta L is equal to PL by B2 minus B1 into TE into ln of B2 by B1. Self-weight deformation. Prismatic bar. Gamma is equal to self-weight density. Total weight W is equal to gamma AL. Px is equal to gamma AX. In this case, the role of axial load is played by self-weight, and at any section, the axial load is the self-weight of portion which is below the section XX. If we consider section XX here, this weight will be self weight. Integral 0 to L delta L is equal to gamma AX integral 0 to L gamma AX dx by AE. Here gamma AX is force that is drawing, dx is the length of that strip we are considering, A is normal one. Delta L is equal to gamma L square by 2E is equal to WL by 2AE. The self weight of prismatic bar is delta. What will be self weight deformation in every dimension of prismatic bar gets doubled? If every What will be self weight deformation if every dimension of prismatic bar gets doubled? Here uh, every dimension is getting doubled, so gamma, if you use gamma L square by 2e, then L is doubled. Gamma 2e will be gamma and E will be same, so delta prime is equal to 4 delta. If we consider WL by 2AE, WL by 2AE, then A will be doubled, L will be doubled, A will be 4 times, L will be doubled, weight will be 3-dimensional, so 8, we will get delta prime is equal to 4 delta. The self-weight deformation of prismatic bar is directly proportional to square of length, so better use gamma L square by 2e only. Gamma L square by 2e only. Find out displacement point C because of self-weight deformation. Because of self-weight deformation C of point C. Here, the interesting point is delta C will be equal to self-weight deformation of AB plus self-weight deformation of BC, and deformation of AB due to BC as a load. BC as a load, there will be deformation in AB also, so that should also be considered. Self-weight deformation is gamma L square by 2e. Self-weight deformation in BC is also gamma L square by 2e. Deformation of AB due to BC is gamma AL of BC, weight L into L by 4AE by which is here a 4a if s diameter is 2 times, then 4a, then we will get 5 by 4 into gamma L square by E. A prismatic bar of length L and cross-sectional area A is rotated in horizontal plane about a vertical axis which is passing from one end. Find out the axial deformation due to centrifugal action if density of material is rho and it rotates with uniform angular velocity omega. Also find out maximum axial stress developed in the bar. A bar is made to rotate along this fixed axis with omega radian per second, and then maximum axial stress developed in the bar. If we consider a section at a distance r, then centrifugal force is equal to mr omega square. Mr omega square, m is rho a l into l at a distance x from free end. Pxx is equal to rho a x into L minus x by 2 into omega square, mr omega square. Fc is equal to mr omega square. Here m is rho a x from free end, and r is L minus x by 2. L minus x by 2, which means from this point to this point, L minus x by 2. L is this length minus this length from this point to this point, L minus x by 2. Okay. From center of mass of this point to the axis of rotation r into omega square. Pxx is equal to rho ax into L minus x by 2 into omega square. So the centroidal L minus x by 2 is centroidal distance of mass m from axis of rotation. Delta L is equal to integral 0 to L p rho ax into L minus x by 2 into omega square into dx by A is equal to rho omega square by E into integral 0 to L Lx minus x square by 2 dx is equal to rho omega square by E into L cube by 2 minus L cube by 6. Delta L is equal to rho omega square L cube by 3E. For axial stress Pxx max dPxx is equal to 0, x is equal to L. P max is equal to rho A L square omega square by 2. Like at what point Pxx is maximum, then we have to, it is at x is equal to L, which means at x is equal to L at this end force is maximum. And delta L here, this is total. Delta L is rho omega square L cube by 3A. Rho omega square L cube by 3A. Three masses m, 2m and 3m are attached to a circular cross section and rotate about vertical axis. Frictionless rod at omega as shown in figure. Consider the masses must to be concentrated at that point itself. For a equal stress in all three rods, the cross-sectional area of rod in three segments will be in ratio of no, due to this force Fc3, Fc2, Fc1. Fc1 is equal to m into 1 into omega square. Fc2 is equal to 2m into 2 into omega square and 9m omega square. Fc3 9m omega square. Sigma 1, which is here, is equal to Fc1 plus Fc2 plus Fc3 14m omega square by a1. Sigma 2 Fc2 plus Fc3 by a is equal to 13m omega square by a2. Sigma 3 is equal to Fc3 by a3 is equal to 9m omega square by a3. Sigma 1 is equal to sigma 2 is equal to sigma 3. Then a1 is equal to as it is given that equal stresses in three rods. So a1 is to a2 is to a3 is equal to 14 is to 13 is to 9. Okay, now for conical bar, axial load distance x is equal to weight of small cone. Integral delta L is equal to integral 0 to L gamma into 1 by 3 ax into x. That is volume of this part x at a distance x from tip. Dx by ax into E. Delta L is equal to gamma L square by 6E. Bar of uniform strength. A bar is called a bar of uniform strength if value of stress remains same along length of bar. For example, external load due to W, there will be sigma is equal to W by a constant from top to bottom. Due to self weight, gamma sigma x x equal to 0, sigma is equal to 0, sigma xx is equal to gamma L at this point. Gamma sigma xx is equal to gamma x by x is equal sigma xx is equal to gamma x, which is linear like this. If every dimension gets double, sigma prime max is equal to 2 sigma max. Okay, combining these two, in actual it will be like this: bar of non-uniform strength. Composite or compound bar. For example, there is a solid rod and a hollow shaft. A solid rod of ASES, hollow shaft of AHEH. Then a load P is applied. This is collar. A load P is applied. P is total force here. PS is over here. PH in non-hollow part. PS is equal to load shared or resisted by solid rod. PH is equal to load shared or resisted by hollow shaft. By static equation, P is equal to PS plus PH. By compatibility, delta L has is equal to delta LH. PSL by AS, ES is equal to PHL by AL, EH. A composite column with cross-sectional area 0.25 meters square is made by concrete and is reinforced by steel bars of diameter 25 mm and they are 12 in numbers. Find out maximum axial load that this column can bear without failure, given E steel is equal to 200 gigapascal, sigma allowable is equal to 70 megapascal, E concrete is equal to 25 gigapascal, sigma S is equal to 8 MPa. AS is equal to 12 into pi by 4 into 25 square is equal to 5890 mm square. AS is equal to 0.25 meter square minus AS. Okay. Yes, then it will be 244110 meter square. As total cross sectional area is given. Okay, Pmax is equal to maximum axial load that column can bear without failure. Pmax is equal to Pmax C plus Pmax S is equal to sigma max C plus sigma C max C into AC plus sigma max S into AS. Compatibility delta C is equal to delta S, as it is composite bar. Delta C and delta S both should be same, steel and concrete. Sigma S L by ES is equal to sigma C L by EC. Sigma S by C sigma C is equal to ES by EC is equal to 200 by 25 is equal to 8. Sigma S is equal to 8 sigma C. Case 1. Sigma S is equal to sigma S is equal to 70 MPa. Sigma C is equal to 70 by 8 is equal to 8.75 MPa, greater than sigma AC. Case 2, sigma C sigma AC is equal to 8 MPa. Sigma S is equal to 64, less than sigma S. So this can be the correct case. Sigma max steel is equal to 64 MPa. Sigma max concrete is equal to 8 MPa. P max is equal to 8 into that area plus 64 into that area is equal to 2329.84 kilonewton. Find out the value of load W, which is just sufficient to close the gap. The A1 is equal to E2 is equal to 100 mm square. E1 is equal to E2 is equal to E3 is equal to 200 gigapascal. Total delta is equal to 1 mm plus 1 mm is equal to 2 mm by W. What is it? And delta is WL by W by 2 W by 2. Load will be shared by these two. Then W, okay, WL by AE. Let's assume displacement of the bar is equal to delta 2P plus P2. Okay, W by 2 is equal to 2 delta. Okay, 2 is equal to 40 kilonewton. W is equal to 100 kilonewton. What will be vertical displacement of rigid rod? Okay, total vertical displacement is equal to 1.99 mm. It is equal to 30.03 kilonewton. Okay, from workbook, same like these conditions, similar triangles can be applied, similar triangle concept can be applied, and we can solve these equations. Okay, I have demo epsilon z is equal to delta L by L is small equal to 0. General Hooke's law, sigma epsilon z is equal to sigma z by u minus mu sigma x by u minus mu sigma y by is equal to mu into sigma x plus sigma y. Thermal stress, it is secondary type of stress because the primary stress comes due to load only. Experimental results. Delta x directly proportional. These are experimental results. Delta x directly proportional to L. Delta x directly proportional to delta t. Delta x directly proportional to L delta t. Delta x is equal to L alpha delta t. Alpha is equal to delta x by L delta t. Quotient of thermal expansion and per degree centigrade. Steel is equal to 12 into 10 power minus 6 per degree centigrade. Alpha copper is equal to 17 into 10 power minus 6 per degree centigrade. Delta x is equal to L alpha delta t. Epsilon x is equal to alpha delta t. Delta y is equal to H alpha delta t. Epsilon y is equal to alpha delta t. Delta z is equal to B alpha delta t. Epsilon z is equal to alpha delta t. Epsilon v is equal to epsilon x plus epsilon y plus epsilon z. Epsilon v is equal to 3 alpha delta t. If a member is free to expand or contract along any direction, then it will not experience any thermal stress in that direction. Invar alpha is almost equal to 0. Precision instruments use invar. Thermal stress calculations. A prismatic bar is fixed between rigid supports along its length, then L, A, B, E, alpha, delta T. In x direction, increase in length due to increase in temperature is equal to decrease in length due to reaction force R. L alpha delta T is equal to minus R into L plus L alpha delta T by A alpha sigma x is L alpha delta T is equal to minus RL by AE. Yeah, sigma x is equal to minus E alpha delta T. Special case: if L alpha delta T less than delta, then sigma x is equal to 0. If L alpha delta T greater than delta, then there will be a restriction at some point, right? So there will be stress. The L alpha delta T minus delta is equal to minus RL by R. Delta is the gap here, is equal to minus RL by AE. R minus is because there will be compressive stress. R by A is equal to sigma x. Sigma x is equal to minus of E alpha delta T minus E delta by L. Prismatic member fixed in one direction with the uniform increment in temperature will experience thermal stress is equal to E alpha delta T in same direction. A circulated tapered with minimum diameter d1 and maximum diameter d2 is fixed between rigid supports along its length. If temperature is increased by delta T degrees centigrade, then what will be the value of maximum axial stress? Thermal increment doesn't depend on cross-section area, whether it is tapered or not. Increment delta L is equal to L alpha delta T is equal to minus 4RL by minus 4RL by pi E d1 d2. R is equal to minus alpha delta T pi E d1 d2 by 4. R acts at both fixed ends, but because d1 less than d2, sigma is max at d1. Sigma max is equal to minus alpha delta T pi d1 d2 by 4 into pi by 4 d square by 4 is equal to minus E alpha delta T into d2 by d1. Okay, that's how we have to solve. The main point here is increment. If there is due to reactions R will be we get R. From that R we can find this increment L alpha delta T due to compressive. Okay, the prismatic bar AB is fixed between rigid supports at A and B. The temperature increment of bar is having linear variation with 0 degrees centigrade at A to T degrees centigrade at B. Then which one of the following option is true? The stress in bar. 0 at A to the E alpha delta T A to B. Okay, these are options. These are options. Prismatic bar fixed rigid supports at A and B. 0 degree centigrade at A. Then stress in the bar. Thermal expansion of element integral 0 to L delta L is equal to integral 0 to L dx directly proportional del dx alpha tx by L. Tx by L is varying linearly. Delta is L is equal to L alpha T. L alpha T by 2 is equal to minus R L by A. Sigma is equal to minus E alpha T by 2. E alpha T by 2, which is uniform. Reaction at A and B will always be equal. Even though temperature is different at A and B, reactions at A and B will always be equal, and stress is also uniform. Sigma is equal to minus E alpha T by 2. This is how we get it. A dx element, we have to consider dx element, then find delta L, then is they equate it to minus RL by A. R by A sigma, you can write R by A sigma. Then one workbook question, just finding delta A. A square on is fixed within 2 dimensions, applicable for rectangle as well. Sigma x sigma y, due to symmetry sigma x is equal to sigma y is equal to minus sigma x not equal to 0, sigma y not equal to 0. Next direction, increase in length due to increase in temperature and decrease in length due to sigma x sigma y. A alpha delta T is equal to minus sigma x by A minus mu sigma y by E into A alpha delta T is equal to minus sigma by A minus mu sigma of minus sigma by E. E alpha delta T is equal to minus sigma of 1 minus mu sigma is equal to minus E alpha delta T by 1 minus mu. E alpha delta T by. Here the main concept is in next direction, increase in length due to increase in temperature is equal to decrease in length due to sigma x and sigma y. Due to sigma x and sigma y, square fixed in all directions, so total deformation should be 0. By symmetry, sigma x is equal to sigma y is equal to minus sigma. From that we can solve. A cube fixed from all directions, then sigma x is equal to sigma y is equal to sigma z is equal to minus sigma. In next direction, increase in length due to increase in temperature is equal to decrease in length due to sigma x sigma y sigma z. A alpha delta T is equal to sigma x by E minus mu sigma y by E minus mu sigma z by E into A. Sigma is equal to minus E alpha delta T by 1 minus 2 mu. Thermal analysis of composite bar. Two bars rigidly connected face to face, subjected to increase in temperature. Okay, then sigma c is equal to compressor stress in copper, sigma s is equal to tensile stress in steel. At final position, compressive force in copper is equal to tensile force in steel. Okay, first let's see, like copper and steel. Copper expands more because of more alpha. Alpha copper is more, so it expands more. Alpha steel is less than alpha copper, so it expands less. So this copper will be pulling this steel. Due to that, tensile stress will be generated in steel, and this steel will be pulling this copper, so compressive stress will be generated in this copper. Okay, then but force should be equal in copper and steel. At final position, compressive force in copper is equal to tensile force in steel. At that point, they will stop now. So sigma copper into A copper is equal to sigma S into AS. Compatibility equation delta actual steel is equal to delta actual copper, because at both should be at a final point. L alpha delta T of steel plus sigma L by AE of steel is equal to L alpha delta T of copper minus sigma L by AE of copper. All are of copper here. Okay. Um, Case 2. Two bars rigidly connected face to face and subjected to decrease in temperature. Okay, case to case, then sigma C is equal to tensile stress in copper, sigma S is equal to compressive stress in copper. Same as before, at final position, compressive force on steel is equal to tensile force in copper, sigma S into AS is equal to sigma CU into ACU. Compatibility equation, delta actual steel is equal to delta actual copper minus alpha delta T steel minus sigma L by A of steel is minus because it is compressive is equal to minus alpha delta T of copper plus sigma L by A of copper. Two bars rigidly fixed between supports connected end to end subjected to increase in temperature. Okay, if it in the case is like this, steel and copper are connected end to end. Sigma Cu is equal to compressive stress in steel. Sigma S is equal to compressive stress in steel, because that these both are at fixed. They both can expand, but they both are restricted. At final position, sigma Cu ACU is equal to sigma S AS. Compatibility equation, delta actual of steel plus delta actual of copper is equal to 0. Here this compatibility equation is the main one, and which is differing from initial cases. L alpha delta T of steel minus sigma L by E of steel plus L alpha delta T of copper minus sigma L by E of copper equal to 0. Reaction forces are sigma S is equal to minus R by AS, sigma C is equal to minus R by ACU, R is equal to minus sigma CS is equal to minus sigma CU ACU. Case 4. Two bars rigidly fixed between supports connected end to end and subjected to decrease in temperature. Sigma C is equal to tensile stress in copper, sigma S is equal to tensile stress in steel. At final position, sigma CUAC is equal to sigma S into AS. Compatibility, delta actual steel plus delta actual copper is equal to 0. Minus of alpha delta T steel plus alpha sigma L by E of steel minus alpha delta T copper plus sigma L by E of copper is equal to 0. Both will be tensile stresses. Okay, so based on above examples, there are some problems. And there is a gap less than or equal to delta than 0. If there is, then we have to think about final position force will be equal. Then actual steel, actual copper is equal to this gap delta. Okay. Find out stress in A and B block. A is equal to A alpha. Okay, then for reaction forces for at final position, forces should be equal sigma A into AA plus sigma B is equal to sigma B into AB is equal to sigma C into AC. Then we will get a sigma B is equal to 4 sigma A and sigma A is equal to sigma C. Compatibility, delta actual A plus delta actual B plus delta actual C is equal to 0. As A and C are identical, 2 delta actual A plus delta actual B is equal to 0. 0. Sigma A is equal to E alpha delta T by 2. Sigma B is equal to the 2 E alpha delta T. Circumferential or diametrical hoop star hoop strain sigma h. Diameter of wooden wheel is equal to capital D. This is wooden wheel and these are steel rings. Initial diameter of steel ring is equal to small d. D small d less than capital D. Final diameter of steel ring is equal to capital D. This is inside wooden ring. This is steel ring. Like we have that steel ring gets fitted into that wooden wheel. Okay, circumferential strain in steel ring is epsilon h is equal to pi capital D minus pi small d by pi small d. Epsilon h is equal to capital D minus small d by small d. Hoop stress sigma h by Hooke's law, sigma h is equal to E epsilon h. Sigma h is equal to E into capital D minus small d by small d. Hoop stress in a steel ring. Nature of stresses, steel ring tensile, wooden wheel compressive. Uh, uh, Nature of stresses, steel ring is tensile, wooden wheel is compressive. Okay. Sigma W AW is equal to sigma S is minimum increase in temperature necessary for proper fixing. Pi small d plus alpha delta T is equal to pi capital D. L is pi d. Then alpha delta T is equal to capital D minus small d by small d. Epsilon T is equal to epsilon H. Then delta T is equal to 1 by alpha capital D minus small d by small d. An example based on the say above, like a steel ring of 999 mm is to be fitted on wooden wheel of 1000 mm. Find out hoop stress generated in steel ring. Then that is nothing but epsilon h is equal to capital D minus small d by small d. And find out increment in temperature necessary for proper fixing. Delta T is equal to 1 by alpha of hoop strain. Okay, sigma h is equal to E into hoop strain. Okay.